Today we are going to see a theorem on extreme points of a smooth function on an n-surface S. So what is an extreme point? A point on that surface S is an extreme point of a smooth function g if the value of g at that point is less than the value of g at any other point on that surface or greater than the value of g at any other point on that surface. So coming to the theorem says that given an n-surface S, we have a function f such that h is equal to f inverse of c and f is defined on an open subset u of Rn plus 1 to R. And any point on that surface is regular point of f. And given a smooth function g on the same surface subset u of Rn plus 1 and an extreme point of g on the surface S, P. So we have given an n-surface S, a smooth function g on that n-surface, and also an extreme point P of the smooth function g on n-surface S. We have S, G, and P. Since S is given and S is said to be an n-surface, there exists a smooth function f satisfying certain conditions. So the theorem says that if P is an extreme point of G, then there exists a real number, lambda, such that the gradient of f at extreme point is going to be a scalar multiple of the gradient of f at that same point. So given an extreme point P, the gradient of g at that point is a scalar multiple of gradient of f at that point. Coming to the proof, we start with the tangent space of that surface at an extreme point. Let P be an extreme point. Then we consider SP, the tangent space of that given n surface at point P. SP is the set of all tangent vectors of the surface S at P. Let V be an arbitrary tangent vector at P. Let V be an arbitrary tangent vector to the surface S at point P. Then we know that P is the tangent of a parameterized curve on that surface S passing through the point P. Also, we know that we have already assumed that P is an extreme point of G. If P is an extreme point of G, then T naught, we have already seen that alpha of T naught is P. Okay, this is the form of parameterized curve passing through P. So there exists a value on that interval I, T naught, such that alpha of T naught is equal to P. Hence, P is an extreme point of G, T naught is an extreme point of G composition alpha. G composition alpha will have a restricted range. Since G of P is already there in this range, it is going to be an extreme value. Therefore, T naught is an extreme point of G composition alpha. It is quite straightforward. Now we are coming to the calculus actually. So it is an extreme point. T naught is an extreme point, then the derivative of G composition alpha at T naught is going to be 0. Since it is a critical point, it is an extreme point. So applying chain rule, we can say that the gradient of G at alpha T naught dot the velocity vector of alpha at T naught is going to be 0. The derivative can be written as gradient of G at alpha T naught dot alpha dot of T naught. So alpha of T naught is nothing but P, and alpha dot of T naught is nothing but V. We have assumed that V is the velocity vector of the parameteristic alpha at T naught. Therefore, we can substitute the value of alpha T naught and alpha dot of T naught as P and V. Therefore, we have these two vectors are perpendicular. We have assumed an arbitrary vector from the tangent space and obtained that this vector is always perpendicular to the gradient vector at P, the gradient vector of G at P. Therefore, the gradient vector of G at P is going to be perpendicular to any tangent vector or all the tangent vectors. So SP perp. Gradient of G at P is going to be perpendicular to the set of all tangent vectors. And we have seen in this case of tangent spaces, we have seen that the gradient of f at P, the space of nabla FP perp, is the tangent space SP. So if this is the case, then we can say that SP, the tangent space SP, is a hyperspace of dimension n in Rn plus 1. And the set of all vectors perpendicular to SP is going to be a one-dimensional space, and gradient of FP is a vector in this space, and therefore we can span this space using gradient of FP. So SP perp is a one-dimensional space spanned by gradient of FP. Therefore, any vector in that space is a scalar multiple of gradient of FP. Therefore, since gradient of GP belongs to this space, gradient of GP is a scalar multiple of gradient of FP. So this is the proof of the theorem we have seen. This is an important theorem to check extreme points of a smooth function on an end surface. Given an end surface and a smooth function on that surface, you can do the same in 3-dimensional, 4-dimensional surfaces. Given a smooth function on a surface, you can compute by verifying the given a surface. We have a function f, and given a smooth function g, we can compute the gradients of f and g at different points, and we can compare whether g is a scalar multiple of f at that point, whether gradient of g is a scalar multiple of gradient of f at that point. If it is so, then that point is a potential extreme point of g on that surface. If it is not, this is not going to be an extreme point. So this is an important tool to check whether a given point is an extreme point of a smooth function, or we can compute the list of all potential points that can become a minimal point or maximum point with respect to a smooth function on a surface.